Today we're going to take a look at section 3.3, which is the theory of equations. There's only one slide here that has a significant amount of writing, but there is a little bit on the first slide here. This slide talks about something that we've touched on before and goes a little bit further to define one more fact. So if we have a factor x minus c, remember we were working on that with synthetic division last time, and it occurs k times in the factorization. So what that means is that there is an x minus c and it has a power of k. It occurs k times. Then c is a root of the polynomial. We already talked about that. The new part is that it tells you it's with multiplicity k. That's sort of a new vocabulary term, with multiplicity k. All right, so our first two examples are really nothing more than identification type examples. They're things we've done before with this one extra layer at the end added on, that it's identifying the multiplicity part. Okay, so here's the first one, two parts A and B. It says to find all zeros. We've done that before, but now it says with multiplicities. So jot the first one down. It's already factored for you. So there's no factoring involved on part A. And what it means then to find zeros is it means, once it's in factored form, to set each part equal to 0 and solve it. So if you were to set each factor equal to 0, it would look like x cubed equals 0, x minus 2 squared equals 0, and x plus 4 equals 0. Right? Now think with me a minute. What happens when we have x cubed equals 0? If I try to get rid of, how do we get rid of a cube? A cube root. And because this is set equal to 0, what happens when I take the cube root of 0? You get 0. So this very first piece is equivalent to just having this say x equals 0, right? Because the cube root would just eliminate itself with the 0. It doesn't change it. And the same is true for the x minus 2 squared. How would we undo a square? We'd square root. So equivalently, it would have been just as nice for me to write this down, actually. Let me just change the size of this. Without the squared on it, because it doesn't change anything, right? Okay, so let's solve these three simple equations. The first one's actually already solved for us. And then we'll do the one little extra piece that our previous slide talked about. What does x equal in the middle one? 2. And on the third one? -4. Okay, so we've found the zeros. In parentheses it says with multiplicities, right? Okay, so over here it says the multiplicity is simply k, which is the power or the exponent, right? It's just what it's raised to. So taking a look at our first example, what is the multiplicity of x equals 0? 3, right? Because it was raised to the power 3. What's the multiplicity of 2? 2, because it was raised to the power 2. And then what would be the multiplicity of -4? It would be 1. It's not raised to a power, or it's an understood power of 1, however you want to sort of think about that. It's a power of 1 really on it. Okay, that one was kind of nice because it was already factored for us, and part B isn't. But part B is not too terrible because what do you notice is true about all three terms? What were you saying, Ansley? They do decrease in power, that's true. They all have something in common, right? They all have a common factor, and the common factor they have in common is x to what power? To the third. Actually, to the third. They have all the way up to 3 in this one. So if I take x cubed out of x to the 5th, what do I have? X squared, right? And the next piece? minus 6x, and the last one, plus 9, and it all equals 0. Okay, the first piece is completely factored, right? The x cubed is all good. There's a part in parentheses, though. Can it be factored further? Yeah, it can. How will it factor further? Okay. And x's at the beginning. Good. And it's fine if you think about it this way. That's how we've mostly done it. But you could also condense it, which is a little more helpful for what we're working with in this particular section, and write it as squared. Right. Good job. At this point, this problem looks like the first one was given to us, right? Okay, so what did I do on the first one after I had it all in factored form? Well, what was our step? What would we do? Right, we set each piece equal to 0, and we kind of ignored the exponents, right? Because they don't actually change anything in terms of solving where this is equal to 0. So in the first one, I have x equal to 0. On the second one, I have x minus 3 equal to 0. Now, the first one's done. It's x equal to 0. But I need to know the multiplicity. What's the multiplicity of the first one? It's 3, because it's an exponent of 3. Solving the second one, I get x equal to 3. And what's its multiplicity? It's a multiplicity of 2, because it's x minus 3 cubed. Okay, so the only new thing that I taught you today was the word multiplicity in terms of mathematics, and that it means the exponent on the factor, right? Okay, so hopefully in your mind you might be thinking, but why does it matter? Who cares? I mean, really, right? Okay, so I'm going to have the next slide come up. There's a whole bunch of writing, so I'm going to just pause and let you write everything down. After you've written everything down, we'll talk about it, okay? So just jot these down. This will answer that sort of question of what does it matter? Okay, we're going to talk about these different facts about multiplicity. The first one we're going to actually reference on here is something I've talked about before in class, but not in great length, and nor have I justified it every time I've used it at all. I've just sort of said it. So what this actually says is that if your polynomial has exponent, has degree of 6, then you're going to have 6 zeros. But they may not all be unique. Some of them may repeat themselves. For example, take a look back over here. We'll look at part B because it's all multiplied out. What's the degree of part B? The degree of the polynomial. 5, right? Degree just means highest exponent. We've talked about that once before. It's a degree 5 polynomial. So let's take a look. There sort of looks like there's only 2 answers, x equals 0 and x equals 3. And that's true. There's 2 distinct answers. But the first one occurs with multiplicity 3. There are 3 zeros at x equals 0. There are 2 zeros at x equals 3. That's a total of 5 zeros. And it's because it's the power 5. Okay? I've referenced this before when I've said something like, oh, look, we've gotten 3 answers. And we should expect 3 answers because it's a cubic. It's a power 3 equation. That's when I've referenced it before. The same thing happens on part A. I know it's not multiplied out, and we're certainly not going to do that. But if you take a look, this is x cubed. And this in the middle will give us an x squared term as your highest degree because it's power 2, right? So that's 3 plus 2. That's a power of 5 at this point. Times the x plus 4 at the end would be a power of 6. This is an x to the 6th equation if we were to multiply it all out. Okay? And look, there are 3 zeros at x equals 0, 2 zeros at x equal 2, and 1 0 at x equal negative 4. That's 6 zeros. Okay, and that will always happen. Now, these particular ones were whole numbers. Not only were they whole numbers, but they're real numbers is actually what I meant to say. They aren't always real numbers. Sometimes we get complex numbers. So it may take complex numbers before we actually see that we have all the zeros we're supposed to have, but we will have the same number as the exponent. Now, thinking about complex numbers, the second fact here says that complex roots come in conjugate pairs. So let's remind ourselves what conjugate pairs are. If you had a 0 at 7 plus I, what would you also have a 0 at? What's the conjugate? 7 minus I. So even if they don't tell you both of those as the conjugate pairs, if they don't tell you both pieces of it, you know if you see one, the other one is a 0 there as well. What if they actually just gave you something like 3i? Okay, there's no real number part. It's just the imaginary part. What would also have to occur there? Right, negative 3i. They occur in pairs, and really that's because this is 0 plus 3i. I mean, that's what 3i means. So you have 0 plus 3i, 0 minus 3i, okay? So those are always going to occur in pairs. We're going to see some examples of that. And then the last two facts kind of go hand in hand. They talk about what happens when the multiplicity is even versus the multiplicity is odd. And I'm going to draw you sort of a sketch example. It's certainly not a good graph. It's just a sketch of what's happening on part B. Notice it says that x equals 0 has a multiplicity of 3, right? 3 is odd, okay? So according to these facts here written at the bottom, that means that the graph is actually going to, it's the second to bottom one, it's going to cross through the graph at that value. So over here, if I were to draw, if I were to draw my xy axis, x equals 0 is along the y-axis, right? So along the y-axis, I'm going to cross through the x-axis. I'm going to hit the origin, in other words. Not only am I going to hit the origin, I'm going to cut completely through it. So all I know is that it's going to cut through. I don't know how exactly. I mean, I don't even know, because based on what we've talked about, if it's going to go up or if it's going to go down. You know, I know, but based on what we've talked about, we haven't talked about how you'd make that determination or how steep or how shallow it occurs, right? I mean, like, it could be doing this. You don't have the equipment so far for us to actually make that assessment. However, I can tell you that the bigger the number, the more sharply it goes through. Okay, the coefficient plays a little bit in there too, but if you just had a power of 1, it would cut through it like this. It would look an awful lot like the graph y equal x. Because this is actually cubic, right, it's an odd power of 3, it's going to cut through it more like this. And if it were a power 5, it would be even more exaggerated, where it's flattened out. Okay? It's not a real important fact. I just am letting you know that they do look different depending on the powers, but they'll still all cut through. Okay? So my best guess is it looks something like this. The next thing I know is that over here at x equals 3, I have another 0. But it's even because it's a multiplicity 2, right? So over here, when it's an even and it's a multiplicity 2, it doesn't cut through the graph. It actually will bounce off the graph. So, okay, so what does that look like? Well, it'll have to first come back up, otherwise it would never touch the x-intercept, right, the x-axis, and it will bounce off. So it'll look something like that, okay? Because it's an even multiplicity. Again, depending on how big that multiplicity is will depend on how flattened it is that it bounces off at. This is a power 2. It's going to look kind of like a parabola. If you zoomed in really close around that spot, it'll look like a parabola. If it were, if it were an x to the 4th, it would have more of a flattening to it. It would look sort of flatter around that spot. And again, if it were x to the 6th, again, it even would look flatter. But we have something that looks like this, and it would bounce off and it would go back down. Okay, again, you don't know whether it's going up and down. I do, but we'll talk about that later. Okay, so for right now, we're just talking about what's happening as it hits the axis. Okay, we're going to do some examples now of how to use some of this information in the reverse way. Okay, so on this example, you were given the polynomials and you were asked to find the zeros. Now you're going to be given the zeros or the roots and you're asked to find the polynomial. Okay? So the first thing you need to know is that this is a polynomial equation, which means you need to give it a name. If you want to call them all y equals, more power to you. If you want to write down f of x equals, that's fine too. So whatever name you want to use is fine. I'll go with y equals on this one. But in order for it to be an equation, it has to have an equal sign and two sides. The next thing is that each of these values becomes a factor, right? We said that if we have x minus c as a factor, then it means c is a 0 or a root. So over here, if these are zeros, then it means that x minus 2 is a factor. What else do I have as a factor? X minus 4. And what will I do differently on the last one? Right, it'll be x plus 3 because x minus a negative 3 would make it positive. So the signs change when I do the factors from the zeros. This is actually the equation that you're looking for, but it's not in a simplified form. Many of you did something on the test that was a little bit unexpected to me on a problem where you multiplied something all the way out. So I know many of you are very good at multiplying these out, but that's what we're going to do. We're going to finish multiplying this particular problem out. So we take 2 at a time, and there will be cases where it matters maybe which 2 we pick, but in this one it doesn't. So we're just going to move from left to right. And if we're multiplying out and we FOIL, because it's a binomial times a binomial, what do we get? I'll start you out. X squared. What's next? Okay, on the outer side we have negative 4x, and then minus 2x plus 8. Now, in the midst of multiplying that out, please don't forget, please write down the x plus 3 right next to it. Because if I'm saying that one step is equal to the next step, they really need to be equal, which means not missing any of the pieces, even if I'm not working with them yet. Okay? We are going to multiply these again, but it probably would be easier if we cleaned up that 4 piece in the middle there at the beginning, in the parentheses at the beginning. So this would be x squared plus what? What do we have next? Negative 6x plus 8. Now we have a trinomial times a binomial. I know we've encountered these in class before, but let me just make a reminder to you of how I choose to do them to keep track of all my terms. I usually take the first term in the trinomial and then multiply it by everything in the next set. And then I'm done with that piece. And then I go to the second term in the trinomial and do that by everything in the next set. So that's how I'm going to process through mine. If you choose to do it in a different order, that's okay. Just be careful and have a pattern of how you're doing it. So if I have x squared times x minus 3, that will give me x cubed plus 3x. And in some sense, I'm sort of done with this piece now. And we're going to move on to the 6x piece. So negative 6x times x plus 3, what do I get? I did this in my first class. I left my squared off there. I am so sorry. X cubed plus 3x squared. I've made the mistake twice now in a row. Okay, what did you tell me? What were you telling me, Amos? Minus 18x, right? Okay, so we're done with the negative 6x piece. Somebody else help me with the last piece, the 8 piece. Plus 8x. And then plus 24, yeah. Okay, again, you know, there's nothing wrong with what I've got right here. It's just not simplified. There are things we can combine, right? So I can't combine anything with the x cubed. That's standing alone. But what else do I have? The x squareds can combine. How many of them will I have if I combine them? Negative 3x squared. And then what about my coefficients with an x in them? What do I have? Negative 10x and then plus 24. Okay, and the answer includes the y equals the beginning, or whatever name you gave it. All right, take a look at the next one. See some conjugate pairs there, right? I actually wrote it out for you on part B. We've got a 9i and a negative 9i. Okay, give a name to your function. For a variation, I'll call this one f of x. And they start out the same way. I need x in the beginning of a polynomial, and then I need to subtract what I'm told are my zeros. So what is this going to say? X, what will be the first one? Yeah, it would be plus 9i, and the other one would be minus 9i. And I hope that when you look at that, you remember that that's a difference of squares. You see, the middle terms, the inside terms, and the outside terms match, except for the sign. And the reason that matters is because that means they'll cancel out, or they add to 0. So I really only have the first terms multiplied and the last terms multiplied when I have differences of squares. So first terms multiplied gives me x squared. What happens when I multiply the last terms of these together? You are going to get an I squared. What else are you going to get? A negative. And what's the coefficient going to be? 81. Yeah. Okay, and Amos, you mentioned that the I squared is equal to negative 1, right? So if I have negative 1 replaced here, that's not divided by, but if I'm replacing it with negative 1, what will this end up actually equaling? Positive 81, right? So this is f of x equals x squared plus 81. Is everyone good with that? All right, how many zeros do they tell you you have on part C? 2. How many zeros do you really have? 3. What's the zero that's missing? I. It's a conjugate pair. Only the complex numbers occur in pairs, so we don't have to worry about the 4. It has nothing to do with conjugates, right? But the i's do. So they give me a negative I, so I'm going to also have a positive I. I need a function name. I'll call this one g of x. All right, the first term's a 4, so what's the factor that occurs representing that 0? X minus 4, exactly. How about with the negative I? X plus I. And the positive I? X minus I. Now, I mentioned on an earlier problem, it doesn't usually matter. I mean, in fact, it doesn't really matter at all. You can always multiply from left to right if you want to. But it's going to be a lot easier if you multiply the conjugate pair ones together first. Your workload, your amount of stress in getting things right, you're just going to have a lot less work. Okay? So we're going to multiply these two together first, which means I'm simply going to rewrite the x minus 4 at the beginning and leave it. Now these two, they're conjugate pairs. So as I look at the pieces, this one, the inside, and this one, the outside, they match, and they're adding to 0, right? So I really only have the first terms multiplied, which is x squared, and the last terms multiplied, which is minus I squared. And what is that actually equal to when we simplify? Plus 1. So this is x squared plus 1, and that's actually very friendly on this problem because that ends up being a binomial times a binomial. Less to multiply out afterwards, right? So we like that. And we're going to multiply. We're going to FOIL. So if we FOIL this out, what do I get? First term is x cubed. Outer term is plus x, actually, right? Plus x. Inside is negative 4x squared, and our last term is negative 4. You can stop here. There's nothing wrong with this particular answer. But some of us have this weird thing in our head that says that there's something wrong with this, and we might want to do something else. Ansley's nodding her head. I have that thing going on in my head, too, so I understand it. What might we want to do that makes this look more pleasing to the eye? Yeah, put them in decreasing order. So if you are one of those people, then you're welcome to reorder them. You do not have to. They are fine if they are left the way before, okay? Either of those answers would be sufficient. I guess we should probably write g of x equals. Okay. We have one more example, by far the hardest example that we've done, okay? How many zeros do they tell you you have? 2. How many do you really have? 3. What is missing? 7 minus I. And I'm going to write these together, like when I write the factors out, I'm going to write them beside each other because we want to multiply them together before we mess with the 3 part. So a name for this function, how about a of x? Because you can name whatever you want. This is a little tricky. It looks a little weird. I've got an x, and I need to figure out what I'm going to write next, but it's a 2-piece part, right? It says 7 plus I. It's not just 7 or just I. So when I write this out, I have to put a minus, and I have to subtract from it all of what I have, which is 7, which one I have, plus I. We'll clean it up in a minute before we start multiplying. So if I'm going by that, what would the other one look like? The one at the end, the 7 minus I one. Right, x minus and then 7 minus I. And then what else do I need? X minus 3, right? Okay, so before we start multiplying, simplifying, cleaning things up, whatever, let's just clean up inside of the individual parentheses we have. In other words, distribute negatives. So this is x minus 7 minus I and x minus 7 plus I. And then I still have the x minus 3. Is that okay with everyone? Any questions about what we did? Okay. Yeah.
Why the minus?
good question. So if I were to have, let me use an example with the 3. 3 being a 0 means that x equals 3 is a solution. And we did this last time a couple of times to show that basically if I were to rewrite this and move the 3 to the other side, that x minus 3 would become a factor. That's where it's coming from. It's the fact that we're moving it back to the same side of the equation as the x. Yeah. Good questions. Any others? Okay. This multiplication's the worst we've had because how many terms are here? 3. And how many terms are in the middle parentheses? 3. And if I multiply 3 terms by 3 terms, I end up getting 9. Actually get 9. Yeah, I'm going to get 9 terms just from those 2 pieces alone. So that's where we're going to start. We go through it very much like the other ones, though. I take the first term, which is x, right here, and I multiply this x by everything in that middle set of parentheses. So if I do that, that gives me x squared. What does it give me next? Good, minus 7x, and then plus ix. Plus ix. That's multiplying this x through this entire parenthesis. Okay? Now we're going to do it with the negative 7, the second term here. So I've got negative 7, and it's going to distribute through the parentheses. So what is that going to give me? Negative 7x. Ooh, good, plus 49. And then minus 7i. Lovely. So the negative 7 term's done. And now I have the negative I that I'm going to distribute through. What will that one give me? Negative ix. Okay, good. Plus 7i on that one because it's a negative and a negative. And minus I squared. And don't forget to rewrite the x minus 3 at the end. Okay. So the bad part's done. The good part is many of those things either simplify to 0 or combine. So let's find the ones that simplify to 0 first. Tell me 2 values that simplify to 0 here. Okay, let me find another color. Plus ix and minus ix. Those 2. So those 2 add to 0, right? Is that good? And what else did you find? The 7, which one? 7x or 7i's? The 7i's, right. So this negative 7i and this positive 7i also add to 0. So all of a sudden, originally I had 9 terms, and now I'm down to 5. It's definitely a step in the right direction. Fewer things going on. All right, so let's combine what we have left then. So nothing combines with the x squared. But then what do I have? I have negative 14x, so that's the 2 negative 7x's. I have a plus 49, and I have a negative I squared, and I contend that they combine. Why? Yeah, the negative I squared at the end is actually the same thing as plus 1, right? I squared is negative 1, and this is negative I squared, so it's positive 1, so yes, I have a plus 50. But then I still have to multiply by x minus 3. But, I mean, it's not 3 terms by 3 terms, right? It's 3 terms by 2 terms, which means I'll have how many terms? 3 times 2 is 6. 6 terms when I'm done, so that'll have 6. All right, so let's multiply that out. I have x squared times x is x cubed. X squared times negative 3 is negative 3x squared. Look, I got it that time. That one's done. What's next? Good, negative 14x squared. Plus, yeah, it is 42x, good job. And then the negative 14x term's done. Now we have the 50 term. What do we have? Plus 50x and minus 150. Very nice. Are there terms that combine? Yes. I've got my x cubed. It doesn't combine with anything. Then what do I have? Negative 17x squared plus a bunch. 92x and minus the 150. And the name of our equation that I had used was a of x. Any questions on that?